Dr. Margenot is a soil scientist and biogeochemist who joined the faculty at University of Illinois Urbana-Champaign in 2017, where he is currently associate professor. Dr. Margenot leads a research team that combines soil science, agronomy, and biogeochemistry to optimize the agronomic and environmental sustainability of Midwest agriculture. Please join me in welcoming Dr. Margenot.
Well, thanks for having me. So I'm glad to share the results of a couple years in of a few NREC projects on phosphorus. And I want to focus on this in terms of the theme of the big picture of phosphorus. I would argue phosphorus is sometimes more complex than nitrogen, and that's because of how it behaves. It's a little bit more sticky. It can have a lag effect, and that presents some challenges that are unique to this compared to nitrate. So I'm going to talk about the big picture in terms of the overall budget. Where's the P coming from when it comes to P loss from the state? This is funded by 2 NREC projects, and it's being done by a team of students and researchers, largely over there. It's thanks to them that this work is possible, so thanks. And also, I want to point out that we've leveraged the NREC investments to bring about $250,000 and then some in funds from U.S. Soybean Board and NCGA. So thanks to the funders for this. Big picture, this is the MRB. This is where we live. And as you probably know, we have a phosphorus loss problem. This map, I think, shows the scale of the challenge pretty well. Darker brown connotes more phosphorus losses. This is total phosphorus. This is not DRP. This is total phosphorus. And this is across point source and non-point source. And if we think about some numbers here, translating the legend into units that I think are more tractable, we've got roughly about 0.7 pound of P per acre. It's not P205. That would be times 2.2. But this is just P. So we are losing about 0.7 pounds of P per acre across the 31 states that drain in the basin. And if we think about the upper MRB, that's where we find ourselves here today. This is the, quote, worst offender, according to the USGS, just meaning that the highest P loads are coming from this sub-region of the entire basin states. I think this makes sense. We all are aware of this. That's about 1.2 pounds of P per acre, so almost double the average. And our state is roughly from 10 as high as 16% of the total P export to the Gulf of Mexico. So Illinois is responsible for a pretty big chunk across all these states. These magnitudes, I think, are important to start with, because then I want to talk about, well, where is this peak coming from? And if you take away one thing from today is that it could be phosphorus from inputs from the 1800s. Some of it is contemporary losses, and some of it is from stream banks. And parsing out what is responsible for what is a key challenge to making sure that we achieve our goals on P loss reductions. Some terminology here. So last year I talked about legacy phosphorus. I want to correct myself. Not all things that we call legacy P are actually legacy phosphorus. There's evidence, in fact, we published this piece arguing that we should be careful with the terminology. So this is why it matters. Legacy phosphorus, as shown on the left-hand side, typically is in reference to the watershed scale. So there's a legacy of phosphorus that is in the system, soil to water continuum. Residual P is the residual left over from a past input of phosphorus, manure, MAP, or DAP, and that could have been from 2 years ago or from 1,000 years ago, presumably, and there's some studies that show that for some sites. And I'll talk about both of these because our 2 NRECs that I'll talk about today deal with legacy phosphorus on the left as well as the residual phosphorus on the right. Residual is more of a soil focus, and it can be considered to be part of the legacy P challenge, but they are distinct. So let's talk about the first one, the legacy phosphorus, and specifically some of the drivers of legacy phosphorus in our riverine systems. This is a cover of a journal that we made, we made the cover of this journal, excuse me, with the piece that we published on streambank erosion. And if we hone in on this, this is from the upper Embera. This is on Polecat Creek, for those of you who know Coles County. It's a bluff that is sloughing off, and it's sloughing off because of the small creek in the foreground that is chewing away at the bluff. And so as a bit of background here that I think a lot of you know, streams meander. They try to find the lowest point in the landscape, and that's driven by gravity. It's hard to beat gravity. Water will follow gravity's force. And as these streams try to find the low point in a very flat landscape like ours, there's no clear winner. So they'll keep on snaking back and forth, trying to find, hopelessly, that low point, and in doing so, they slough off their banks. Now, that sediment will enter the stream system. It can be redeposited downstream. So bank erosion is not a net total P loss right away, but now we've got phosphorus that's in the water system, where it can chronically give off DRP over time. This happens a lot suddenly when we've got what's called mass failure, the undercut of the bank. As you can see from that left-hand side, it chews away, and then all of a sudden the whole bank collapses. So a lot happens all of a sudden, meaning timescales of measurement should be on the order of half century or decades, not annual. The point here is that these soils have phosphorus in them naturally without any P inputs as MAP or DAP, and so most of the P that we're losing with bank erosion is not from fertilizer. And what's more is that this is the gift that keeps on giving. This is the legacy part of stream bank erosion. Depending on the forms, what we call the speciation of phosphorus in stream bank soils, there's going to be different release rates of phosphorus, and that's what the figure here shows. You've got a pulse of dissolved reactive phosphorus right away upon bank erosion. Think of the Bray P pool. And then you've got other forms like calcium P, iron P that will dissolve very slowly, and that time could be conceivably decades, if not longer. Now, why am I bringing up this legacy effect of the chronic release of P from these eroded sediments? Well, it might explain some of what we're seeing in recent reports from the NLRS. We just saw that we saw a 35% increase in phosphorus losses as a 5-year average. But we also know that we have a negative phosphorus balance across farmland in this state since the 1990s, meaning that we've been putting on less phosphorus as a fertilizer than what's coming off of fields with the harvest of bushels of grain. A negative balance, right? We're mining soil phosphorus. So this seems like a paradox, right? How are we losing phosphorus, or rather, how can we be seeing a 1/3 spike in P export when we've been mining soil P or are in a negative P balance crop-wise? Well, it could be that these sediments that were engendered or they were deposited years or decades ago are still giving off this phosphorus. So this is why the legacy effect of these sediments upon eroding into the stream pose a challenge. Okay. So let's talk about some recent work that we've been doing in the past year as part of this NREC. We wanted to understand what states across the MRB understand or quantify or even just acknowledge, just say the words, bank erosion. And we went through all the state strategies, a few are shown here, and we looked at also the updates to the state plans. So most states update every 2 to 3 years, so we looked at the original and then the updated plans. And what we find is that basically no single state has a number on stream bank erosion, just the erosion of banks, nor then the P that is loaded because of the bank recession, the eating away of the banks. Now, some states do at least acknowledge it, and that's important because that's the first step to quantifying, well, how much of the budget is from this process, and our state is one of these. But then there's some states, as we can see, that don't even say the words bank erosion. So why does this matter? Well, it matters because of how we calculate non-point source and how we interpret non-point source as. So non-point sources are hard to measure. That's why they're non-point source. They're diffuse. There's not a thing or a clear place to measure them. So what we do typically is that we can know the total that exits the state, in this case from a super gauge from USGS. That's the total P export. We know the point sources because by law they have to keep permits on their discharge. That's on a monthly basis. So you subtract the point source from the total, and by difference you derive the non-point source. And I'll pick on our state's plan. The problem is that we then sometimes equate the non-point source with agriculture, and I think that's incorrect, because we know that there are non-ag, non-point sources, and stream bank erosion is, I think, case in point. Now, the reason why our state plan does this is because there was no data at the time, and we're trying to get that very data. So I'm not blaming here, I'm just pointing out that I think we often make this fallacy of equating non-point source with agriculture. They're not the same. Why does this matter even more if we go a higher level up? Well, because we don't quantify stream bank erosion contributions to P-loads across any state in the MRB, there's 31 states, not a single one quantifies it. It means that we're going to be overestimating ag's contribution. This is not exonerate ag. I think I've been misunderstood a few times in a couple of talks on this. It's just saying that to the extent that our P-loads are coming from bank erosion, they're not coming from fertilizer. Some consequences. One, we're going to overestimate ag contributions. We're going to miss a chance, I think, to manage a source of P loss that might be reduced, and I'll talk about that later, through things like drainage. We might be, as a result of number two, misdirecting resources. And I think most importantly for policymakers and the greater public, expectations on drawdown, on improving our P losses, that may not be realistic because of these lag times. It might take 50 years to see a decrease in P. Okay, so the question has been raised, I think, in past meetings like this one and in other talks, well, isn't ag indirectly contributing to bank erosion? And the answer is probably in some contexts and probably not in others, and it kind of depends. So the argument here is that because of how we've modified the hydrology of these landscapes through things like ditches and tile drains, we might have increased the flashiness of streams. So when it rains, the stream flashes with more power, and that will slough off more of the banks. And that would be an indirect way that stream bank erosion is, in fact, partly due to ag. So the evidence out there is that tile drainage has mixed or opposite effects on stream flashiness, meaning that we can't just say that stream bank erosion is always being exacerbated by tile drainage. Here's a recent study that came out of Indiana last year. And to walk you through this, they are using an index of stream flashiness called the RB index. So as that number goes up, there's more flashiness, meaning there's a rain event and the stream surges very quickly and more powerfully. And then on the x-axis, you've got more tileage. And they had a very crude, albeit the best possible, they did a good job, I think, a metric of tileage frequency in the watershed. So basically, as we go from left to right, we get more tiling. And at the very top, we've got two panels. On the left is low infiltration soils, so high clay, low slope, and then you've got high infiltration, so less clay, more sand. And what you can see here is that in soils that don't infiltrate that well, you get less flashiness with tile drainage. That's a good thing for stream bank erosion. Stream bank erosion, this can be attenuated, it can be decreased by more tiles in these situations. And the mechanism is that if soils don't infiltrate well, then tiles help pull the water down, so we decrease the runoff from the surface that otherwise is driving the flashiness. And in the other context, in soils that infiltrate well already, then tile adds too much more drainage, so to speak, and we see that there's a trend of more flashiness with more tileage. So this is an example of how soil types, in part, drive opposite effects of tiles on stream power and thus on bank erosion. So again, it depends. We are trying to understand this. So currently, Dr. Zhou from our group is doing a meta-analysis, trying to quantify, well, when and where. So whenever you see lots of studies with opposite conclusions, that is ripe for a meta-analysis to cut through the noise and figure out what is going on. So these are all factors that interact. That's why we can't simply say that tile drains are a positive contributor to bank erosion. In fact, I'd argue that we've overlooked the potential of tiles if we were to manage the drainage intentionally as a way to mitigate flashiness and again be part of the solution to abate bank erosion contributions. Okay, so let's go through some results on what do we know about bank erosion in the basin, in the MRB, and in our state specifically. So we're going to begin big picture, global, ongoing work here. Globally speaking, it seems like 40% of sediments and 31% of phosphorus exported by rivers is due to bank erosion. This is a global average. Studies are from all over the world, largely North America, Europe, and Scandinavia. And that's interesting because that 31% of total P due to bank erosion is exactly the number that Iowa derived 2 years ago, exactly the same amount. So this is just shy of 1/3 of total P exported from bank erosion. If we think about the MRB, if we hone in on this region in a separate study that we're doing with NREC support, we found just 51 studies that quantify bank erosion. Not even P loading from bank erosion, but just bank erosion as a process. And these studies, of course, leave a hole for our state that we're trying to fill. So a couple of findings. One is that these are mostly sub-15-year studies. That matters because of the hot spots, or the hot moments, rather. Stream banks all of a sudden erode. You need multiple decades of monitoring to capture that. So these are often too short, and that aside, we see that there's quite a big range of P contributions from stream banks in the MRB. So in this region, from 2 to 44% of P export is from this process. Now, on average, this is the amount of 0.7 pounds of P per acre. And that is, if we go back to that slide, exactly how much the MRB loses. I'm not saying that our P losses across the MRB are all from bank erosion, but the magnitudes are up there. They're in fact exactly the same, 0.7 pounds of P per acre from bank erosion from these studies, and that's what we also know from USGS, what the basin is losing on average. Okay. So let's talk about the work that we're doing to try to fill this gap. There's just not data yet, and that data is necessary to inform the state's NLRS and then inform, well, can we deal with this? If so, how? Stream bank erosion is not fun to measure. You've heard some examples of how arduous it is, and there's a scaling problem. It's a pain to put out erosion pins. Ask Allison and Carlos how much work it is to do this. So we're combining or refusing different methods to enable scalability for a statewide estimate that is also sensitive to the Huck-8 scale. So basically, pins that we put in, these are rebar that you slam into the side of the bank, and then you measure the amount of the pin exposed over time. That's the rate of bank retreat, and thus bank erosion. And we can also get fine scale, as you just saw from the previous talk, in this case from laser scanning. This is not on a drone, it's stationary, but the idea is the same. We get millimeter sensitivity. And then we can use things like LiDAR scans, which are more contemporary, post-1990, and then go back and use imagery from 1930s to look at multi-decadal bank erosion patterns. This is what the pin work looks like. These pins are put into different layers that we think have different amounts of phosphorus, and we're also measuring the actual phosphorus in the banks. Most studies don't do that. This is our coverage currently. So we've got, I would estimate, 90% of our sites pinned up. That's the map on the left. So far we have 306 sites across the states and 9 of our Huck-8s. So we chose 9 Huck-8s that capture the overall diversity of the state's Huck-8s. So things like slope and soil type and land use. And a few observations here. So across these 306 pin sites where we're taking measurements on bank recession rates, overall, these banks are fairly tall, about 9.5 foot tall on average, and they're losing about 8 millimeters of soil per year. So they're receding by 0.3 inches, per month, excuse me. So times 12, do some math. I'm not great at math, I'll let you do it. It's over an inch per year. Now, what's left to be done is now measuring in every single sample, we're talking thousands of samples over this project, total P content, and then the form of P. Because the form of P tells us the lag times that we might anticipate, and the total P is important to look at P export loads. At the same time, we're going back in time. So these are examples of images. This is from 1938, where we can look at the current channel of the stream versus what it was. In yellow is 1938, red is 2020. And the center line of the stream shifting tells us that the banks also shifted with the sloughing off. Again, this is the entry of the sediment with the P into the system and might be redeposited downstream. And we're using some of the same sites at which we have these pins as a way to validate the historical imagery so that we have more confidence going back to the 1930s, so 90 years of bank erosion, how accurate is that? So we come back to this. This is, I think, the watershed scale that we're trying to work on bank erosion. Let's talk about now the soil-focused approach. And the proper term here, the term of art would be residual phosphorus. Phosphorus left behind from a past application. It could be from last year. It could be from 10 years ago. All right, so the way that we tend to get at the residual phosphorus, which is part of the Legacy P challenge, is balances. You know what's going in and you know what's going out. This is overly complex, but it gives you a flavor for what is needed to determine the residual phosphorus quantity, how much is there. I'll make it more concrete with an example from the Morrow plots. As you know, it's on our campus, the second oldest continuous study established in 1876, and we've got really good records beginning in 1888. So we have 133 years of good records, 145 years at the time of sampling for this figure of data. So we know what's going in and we know what's going out, and we've got 3 of the 24 treatments shown here. To walk you through them, so we've got the x-axis is time, y-axis is the p-balance, and there's that 0 line. So if you're above that line, you're building up phosphorus. If you're below it, you're mining phosphorus. So the treatment in green would be rock phosphate at very high rates until 1925, and that's what we see as that big increase pre-1920. That's the jump. We've got a large positive balance, but also large uncertainty. So those dashed lines that bound the center line, that would be the max and the min of the actual value, depending on assumptions we have to make in the calculation. So we know that it's high, but the variance is pretty wide. And then the next system is lower input intensity with manure, lower positive balance, and less uncertainty. So we have a challenge here. The bigger the p-balance, the more the uncertainty typically. And then the system that has the least uncertainty is that way because there's no inputs. This is corn on corn, never fertilized once in 145 years. Still gives us 25 bushels per acre somehow. And that's an easy calculation for the balance because it's just grain removal rates. So the key here is how to make a balance have minimal uncertainty to inform action, management, policy, expectations. Well, let's look at a bigger balance. We're going from the Mara plots. We're going to telescope out to the state. This is the state scale from a paper by Lowell Gentry and Mark David in 2000. I've recolorized it to make it more digestible. Sorry, Lowell. And what you see here is that we've got roughly 4.9 billion pounds of phosphorus that they estimate is in croplands, accumulated, meaning residual phosphorus, though they don't call it that. That's a 5% increase over native phosphorus stocks, but it can still be of concern for water quality. Okay, so the question is, well, that's nice. That's a state balance, but where is it? And can we understand in what watersheds is this been built up? That might help explain contemporary fluctuations in P export. How can we do this? Well, we can do this, and this is an update now on the other NREC project. Well, we are lucky to have this archive. I think a lot of you have heard about this. The oldest sample is shown here, 1861 in Perry County, Virgin Prairie is what the label says. And we've got a lot of soils, over 7,000 specifically, sampled across the state from 1861 to present day. We know where they were sampled for the most part, and so by resampling these locations shown on this map, we can try to understand, well, where is the state balance, the positive balance, located? There might be watersheds that are losing more P now, despite farmers not applying more than what is taken off with harvest because of the past residual phosphorus. So knowing where this green stuff is located at a smaller spatial scale is quite important. So what we're doing is that we're understanding baselines and then we're resampling these sites. This map that you're seeing is the baseline. So in the last year and a half, we've been measuring total phosphorus on 7,000 samples, producing this map. This is phosphorus stocks to 5-foot depth. This is before there are any inputs going on. This is what our phosphorus stocks look like. Again, all of that built up P is just 5% more, so this is probably what they look like today. But by resampling these sites, we can understand where in the state do we have this residual phosphorus. The resampling is key because the resampling lets us compare the delta, the change over time. So for this, a map that shows what we've done so far, all the points here in yellow, we have not identified a landowner, and in green, we have identified who owns the land. We've sampled only about half of those. So we've sampled 34 of 453 sites. We know who owns 80 sites. We clearly need your help, and that of others in the state. But if we can even sample, I think, 25% of sites, so about 110 sites, with this kind of homogeneous coverage, we could learn a lot of things about our soils, not just residual phosphorus and its link to water quality, but also basic things like changes in fertility and carbon stocks. Here's a flavor of what the sampling looks like. We go down to 3-foot depth with intact cores, and we measure total phosphorus every 6 inches all the way down to 3 feet. And we do a lot of cores per site. We're doing 8 cores per site, Even though the original samplers took one sample or one pedon, one profile per location, we want to quantify the variability to decrease the uncertainty. So we want to minimize the guessing in the change in phosphorus buildup over time. So here's my shameless pitch. If you know of anybody who farms these sites, you can use this QR code right here. It will show you the Google map. You can click on the map. Here's an example for this point. If we want to click it, you click on the point and you'll get on the left-hand side this panel pop up. You click the bottom Google link in blue, and then it leads you to this submission form and you put in the information. This part is private, and so the person's contact name is not shared with the public. This has been modified since last year. So this is all bottom up. It's all participants like yourselves who know landowners, tenants, etc. Okay, so in summary, to go over a few points here, legacy phosphorus and residual phosphorus are two peas in a pod. They're two components of our P budget that are really hard to quantify, and we've not been able to, both as a state and as a basin, for good reason. It's just really difficult, and the science is now just getting to the point to realize we should be quantifying them. They need to be part of the state budget, and this work that you've just heard about with NREC funding is trying to do just that. The lag times are what I don't want to say concern, they interest me as a scientist. How long until the system flushes out the sediment phosphorus eroded in the 1910s, 1950s? It might take decades or longer. So quantifying that is important. And also in tandem, understanding the complexity of hydrology. We have modified the hydrology with ag. As you've seen, in some cases it helps decrease bank erosion. Sometimes it can increase it. And that's passive tile drainage. So there's room here to intentionally manage our drainage to help solve, or let's say, mitigate bank erosion. All right. So ultimately, the how much and the how long, I think, are going to be key questions, especially as we come up on the 2025 EPA milestone. A lot of the states, in fact, all the states in the Gulf of Mexico basin, or sorry, the MRB, more specifically, they don't have good numbers on this because it's difficult. And 5 reasons why we care about this to finalize. It's accurate accounting. It's just being good on your finances of phosphorus, so to speak. You want to balance the checkbook, what is coming from where. It's a fair way to account for what ag is and is not contributing. And it might be a source of P that we can manage better if we realize that it's happening. Third, we can better direct resources to decreasing this potential manageable non-point source of phosphorus. Fourth, again, very important, I think we need to communicate to policymakers and the public that our P losses are not as quickly resolved as nitrogen insofar as the element of phosphorus is slow. It drags its feet through our systems. It takes a while to draw down. And finally, there's a lot of opportunity here to think about how we can manage tile drainage intentionally. Also things like wetlands buffers, excuse me, to help mitigate the effect of how we drain fields on bank erosion. I don't think that tiles are always going to be a challenge to bank erosion. There's evidence that they can be used to help decrease it. So with that, I want to end with a final update. This was not Julie in the presentation, I know. So this is a development that I was asked to present to the crowd here by my boss, the department head, and by Dean Boyedo as well, the Dean of the College of Aces. The College of Aces has just made a massive investment in what they see as the Morrow Plots 2.0, and they're calling it the alma mater plots. So the next 150 years, the Morrow Plots will be 150 years in 2026. What does the next 150 look like? The sesquicentennial. And what we've been doing for the past year is designing a on-campus site, 64 plots that are tile drained. So there is a monitored center tile and buffer tiles on every single one of 64 plots. It's a large sum of money that was invested. We're talking 7 figures, soon to be 8 hopefully. And the goal here is to understand 16 treatments and 4 replicates. What's the impact on our tile flows, the amount of water, but also nitrate loads and phosphate loads. And I bring this up to you because this stands to be the largest tile-drained replicated field trial in the country, we believe, with 64 plots. It will be part of a new center that is named in honor of George Morrow of the Morrow Plots. And the timeline here is as follows. We're going to begin fall treatments this fall. So we're talking November with things like cover crops for fall application. And then what I would like to do, since I'm leading this effort, is ask the stakeholders of the state, what do you want to see as treatments? So this summer, as a advertisement, if there's interest in reaching out to us directly or myself, or hosting a focus group in your county office, we have a keen interest in hearing from stakeholders, what should we be testing as treatments for these alma mater plots? Once we set these up, we're not touching them for 150 years. In terms of their core essence, we'll modify the rotations, the rates of fertilizer like the marrow plots, but the overall gist of the treatment is going to stay hopefully intact as it has for the marrow plots on campus. So please let me know if you've got any interest and feedback. We would love to hear what you all want us to study here. Thanks for your time. That's all I have.